So problem number 3 on this exam was an Ohanian homework problem, which I also worked out in lecture. So there's really no reason not to be able to get almost full credit on this. Also, to be fair, you did parts A and B for homework, and I added parts C and D. But those are actually relatively easy parts, easy additions. So for problem number 3, you have a uniform disk of mass m, which immediately tells you moment of inertia 1/2 mr squared, and you wrap a string around it and hang a mass little m from it. And you're asked what's the acceleration of little m and what's the tension of the string. Well, actually, parts A and B are integrated. You really have to work them out together, okay, rather than try to separate them. So the first thing to do, this is a Newton's law, although in this case one of Newton's law involves torques and angular acceleration. So the first thing to do is to draw a free body diagram. I'll start with a disk. Since we'll be worried about angular motion, I need to worry about the axis of rotation is here. Radius r, it has a mass m, capital M, I'll indicate that with little feet, okay? And you've got a tension acting on it, pulling down. Now, there's also a support force pulling up and mg pulling down on this, but I told you in lecture, since those won't cause rotation, since they go through the axis of rotation, they apply no torque, we can ignore those to make the drawing simpler, because they won't have any effect on the questions that you're asked. So that's the r vector, that's t. Now, one thing I do have to do is pick my directions, and I'm going to pick positive angular acceleration and positive torque to be into the page. Now that corresponds to a rotation in this sense, okay, like so, if you can see my hand, like so. But remember, a sense or a clockwise motion isn't a direction. Into the page or out of the page is a direction, probably the z direction, depending on your axes. Okay. Now for the hanging mass, little m, there are two forces acting on it. There's gravity pulling down, and there's the tension. Same tension as we have here in the string pulling up, because it's an ideal string. So the tension is the same on both sides. And I'm going to pick positive y pointing down here, because if I pick positive y pointing down, then as this mass falls, which is likely what it's going to do, that will correspond to a rotation of this pulley in a direction into the page, or in this sense around it. So I've connected up the plus here and the plus here to make my life a little bit easier. Okay, so those are the free body diagrams. Those are my choice of axes. Now I'm ready to apply Newton's laws. And to do that, we'll start with the sums of the forces on m in my y direction. And that's easy enough. That's mg down, which is my positive direction, minus the tension up equals mass times acceleration. We'll call that equation number 1. The sums of the torques on the pulley, which I'm calling m, is RT, because remember torque is moment arm, which is arc. R is perpendicular to t, so sine theta is going to give you 1 because theta is 90 degrees. So RT, and this is a positive torque in my positive direction into the page. And that is the only torque acting on this object, so that's I alpha, moment of inertia times alpha. Now, I'll use the fact that the moment of inertia is 1/2 capital mr squared, and alpha is equal to a over r. To simplify this expression for the torque, and say RT equals 1/2 mr squared times a over r. That squared is canceled with that. And so I just have and this r cancels that r, so I just have t equals 1/2 ma. That's my capital M times a. I'll call that equation number 2. Okay. Equation 2, equation 1. So I have 2 equations for 2 unknowns, the tension and the acceleration, and you ought to be able to solve that. And you can do that in a variety of ways, your choice. But one easy way is to just plug this tension into that expression. So plug equation 2 into equation 1, or you could say add them. It's effectively the same thing. So when you do that, you will have, let me just write down, plug t into equation 1. And so equation 1 has mg minus t, but t is 1/2 ma, capital Ma, and that has to be equal to little ma from up there. And I can rearrange terms, take this 1/2 ma to the right, factor out the a, and then just write down the answer. A is equal to, well, mg will still be on the other side of the equation. That's my little m, g, divided by little m plus 1/2 capital M. Okay, all that times g. Okay, I'm sorry, I already have my g in here. I didn't factor that out yet. But I'd like to simplify this for reasons you'll see later. So I'll write this as little m divided by little m plus capital M divided by 2 times g. So that's the acceleration. Okay, one of the things you're asked for in part A. Now to get the tension, plug A into equation number 2, because once I've got A, I can just plug that in here and I have a pretty simple expression. And I'll have T, which as we know is a 1/2 capital Ma, is just 1/2 capital M times little m divided by little m plus capital M over 2 times g. And I've got both the tension and the acceleration worked out. Okay, now part C is one of the things I like to ask, does this all make sense? Okay, so I asked you just for one special case, if the pulley is much more massive than the hanging mass, then you would expect, I hope, the hanging mass just to hang there and not to accelerate down much, if at all. And the limit as m goes to infinity compared to m, little m wouldn't accelerate at all. But let's just say capital M is much, much greater than m. What do our expressions give us? A equals little m over little m plus capital M over 2g becomes, well, if capital M is much bigger than this, I'm just going to ignore, okay, that. There's no reason to worry about that. And so what I have left is, oops, I'm sorry, I don't want to do that. Oh yeah, I do. So what we have left is little m divided by capital M, okay, 2 times g. But remember, big M is much, much bigger than little m, so this number gets vanishingly small. Okay, so it gets small, or 0. Okay, nothing to worry about, and that's what we'd expect. The small mass doesn't move at all. Now, if what's happening to the tension we have above this expression is 1/2 times capital M, little m, divided by little m plus capital M over 2 times g. And if big M is much, much bigger than little m, we'll ignore that little m in that sum. Okay, and so what we'll be left with is, and we'll have a half here and a 1/2 down here, so these halves cancel. Okay, and so we'll be left with little capital M divided by another capital M, so that cancels. And we're left with just mg. The tension is just mg in the rope. And so this also makes sense. That's what you would expect if you just had a mass hanging from a stationary rope. Tension would be equal to mg, because tension and gravity would balance. So these both make sense. I've said it in words as I'm writing, but you would have to explain with just a short phrase or something why these both make sense. Okay, so that's part C. Part D doesn't depend on anything you've done above. This is independent, and you're told to do it differently. Don't rely on the accelerations, etc., that you found. Instead, use energy principles to calculate how fast m is traveling after it's fallen some certain height. Energy is conserved because there are no external forces. Not taken into account with potential energy as gravity is. So I can write down E final equals E initial. Let's assume that the potential energy of gravity is 0 where the little m starts. So that means since it falls, it loses gravitational potential energy, ends up with minus mgh, that's part of E final. It gains kinetic energy, 1/2 mv squared. Meanwhile, the pulley also gains kinetic energy, 1/2 I omega squared. Those are the final energy terms. The initial energy was 0 because everything was at rest and the gravitational energy of little m was 0. Okay, now we need to simplify this. We have v and omega, and we have an I, but we can use the fact that I equals 1/2 capital MR squared, and omega equals v over r to simplify this expression, which now becomes negative mgh plus 1/2 little mv squared. Now we have 1/2 I is 1/2 m r squared. Omega squared is v squared over r squared. Things simplify because this r squared cancels that r squared. And what we end up with is negative mgh plus 1/2 mv squared plus 1/4 capital M v squared equals 0. This equals 0 too. All you have to do is solve this for the velocity. So you have two velocity terms. You can factor that out. You have 1/2 m plus 1/4 big M. And take the mgh to the other side. And you're left with the velocity equals mgh divided by little m over 2 plus big M over 4 square root because we factored out a v squared. And we're done.